Hi, I'm Liz Stuart, a professor at Johns Hopkins Bloomberg School of Public Health. This methods workshop is part of a series being put on by the Johns Hopkins ALACRITY Center for Health and Longevity in Mental Illness. Funded by the National Institute of Mental Health, the center aims to eliminate premature mortality among people with serious mental illness. This webinar series is motivated by the fact that mental health services research, such as that done by the center, requires advanced statistical methods. Challenges of mental health services research includes measurement problems, lack of randomization, and complex systems. This workshop series aims to highlight advanced quantitative methods to help answer important questions in mental health services research. In this workshop, I will be talking about methods to assess and enhance the generalizability of randomized trial results to target populations of interest for policy or decision-making. These methods are particularly useful for when we want to consider the potential broader effects of a program or policy, taking into account any differences between the types of people in a study and those in the target population of interest. Today I'm going to be talking about methods for combining experimental and population data to estimate population average treatment effects. In this section, let's talk about what we mean by population average treatment effects and how we might use different data sources to estimate them. The first thing to think about is what sorts of research questions are we interested in when we're looking at estimating a population average treatment effect. The sorts of questions we're thinking about here are sort of policy and practice questions that relate to a decision that has to be made at a population level. So some examples might be that a health insurer is deciding whether or not to approve payment for a new treatment for back pain, sort of across the board. There might be interest in predicting overall population impacts of a broad public health media campaign around not switching car seats to forward-facing until a kid is 12 months old. Again, sort of population impacts across an entire population. Sometimes that population might be more narrow. So a physician practice might be deciding whether training providers in a new intervention would be cost-effective for their patient population. Or perhaps a healthcare system might want to know whether giving monoclonal antibodies to all individuals recently diagnosed with COVID-19 would be useful. Again, sort of a blanket recommendation. And the question is, what are the effects of that across their patient population? So to formalize this a little bit, all of these questions reflect interest in what I'll call a population average treatment effect. For example, across individuals in a population, does this intervention work sort of on average? I want to note that this population might be fairly narrow. Again, it might be one physician practice, or it might be quite broad. It might be everyone in the United States. A really important point is that there might actually be underlying treatment effect heterogeneity. So this intervention that we're thinking about or studying might actually have stronger effects for some individuals. Maybe monoclonal antibodies are more effective for some people than for others. For our purpose today, though, we're interested in the sort of overall average effect across everyone. We're not interested in saying sort of who should get this treatment or sort of tailoring treatments for individuals. We today are focused on questions that really require learning about the overall average effects across the population. This general topic fits into a broader area of kind of study generalization and concerns about whether results from randomized trials do or don't generalize to, again, to populations or to other contexts. Sometimes this might be because of scale-up problems. For example, if we have a quite labor-intensive intervention, it might be hard to scale it up to a population level. It might be that results don't generalize because of different contexts or different implementation, that once an intervention is implemented somewhere, the intervention itself changes. What this lecture is focusing on are differences in effects in the trial and in the population that are due to differences between that trial sample and the population in the characteristics that moderate treatment effects. So we're sort of setting aside these other problems, the scale up or context or implementation, and focusing today on statistical methods to think through and deal with the fact that sometimes the sample and population differ on these key variables. I do want to make a few connections to sort of some debates or ways of thinking that you might have encountered in your different worlds. First, if any of you work in survey sampling or sort of in survey research, there are very similar issues that I'm talking about here that are coming up in debates around what are called non-probability samples, sort of differences between a formal probability-based survey sample from, say, an internet-based sample that doesn't have a formal probability sampling underneath it. A second note is I do really want to connect back to some foundational work by people like Tom Cook and Don Campbell, who have done decades of work on threats to validity and sort of thinking really carefully about validity and internal and external validity in particular. So there's a long tradition of these ideas, a lot in sort of the social sciences and psychology. And then finally, today I'm using the term generalizability for this idea of generalizing a trial effect to a population. Another term that is often used for this is called transportability. For our purposes today, you can think of these as interchangeable terms. So you might see some literature on transportability, and for our purposes, you can think of it in the same way that we're talking about this generalizability here. Let's spend a little bit of time formalizing these sort of trade-offs of different study designs when thinking about trying to estimate a population average treatment effect. On this slide and throughout, we'll call this the PATE. Again, population average treatment effect, PATE, and I'll just call it the PATE. So to formalize things a little bit with just a little bit of notation, here we're interested in the effect of some treatment, labeled T, on some outcome Y in a well-defined target population. So in this equation, we can see that the PATE is defined as the average across our population of size n. So the summation sign and the 1 over n is taking an average of the difference in potential outcomes. So the difference in outcomes across this population, if everyone receives the treatment, the Y1 term, compared to if everyone in the population receives the comparison condition, the Y0 term. And again, this PATE is just the simple average of those individual effects averaged across the population. So now imagine that I just give you a data set, and this data set has some people who received the treatment and other people who didn't. And we might just say, okay, let's take a difference in means of the observed outcomes between those people as an estimate of our PATE. So this D in the middle of the slide is just the simple difference in the observed outcomes among people who receive a treatment, the Y1 term, and the people who receive the comparison condition, the Y0 term. So then I'm not being super formal here, but we can think about the bias in our estimated population treatment effect, delta, as being just the difference between the true effect, the PATE, and this estimate of it, D. So what we want to be thinking about is how do different design elements, study design elements, affect the size of that bias, the size of delta. And what can be shown is that you can decompose that overall bias into 4 parts. And this will help us think through this generalizability challenge. So we can separate it into 4 parts, 2 of which are due to what I'll call sample selection bias. This is what's sometimes known as external validity bias, and it's basically bias due to the fact that the sample of data we have might not be representative of the population of interest. So the people in our treatment and control groups might differ from the overall population. The second 2 terms are related to what's called treatment selection bias, labeled with the T. And this is the bias that comes in because the people who are in the treatment group might differ from the people who are in the comparison group. Sort of among the people that we have data for, there might be this bias or difference between the treatment and comparison groups. This is often termed internal validity bias. We also can decompose each of these pieces into things due to observed variables, X, and unobserved variables, U. And of course, the differences due to observed things is going to be easier to deal with in any statistical approach because they're observable and we can adjust for them. So again, this overall delta can be decomposed into these 4 different pieces, 2 due to the sample selection bias and 2 due to the treatment selection bias. What this is useful for is that we then can use this to think about how different study designs entail different trade-offs between these sources of bias. So this slide now tries to summarize that. And part of the motivation here is that often in science, we think about a randomized trial as being sort of the ideal way to estimate treatment effects. And that is true if all we care about is the internal validity bias. But it turns out that if we really are caring about this population average treatment effect, our sort of thinking about the trade-offs of different study designs might actually evolve and change. So this table shows that we might have what I'll call an ideal experiment. So an ideal experiment for estimating a population average treatment effect is one where we've randomly sampled people from the population of interest and then randomly assigned them to receive treatment or control conditions. So in this case, all of these bias terms are 0, and we can obtain an unbiased estimate of the population average treatment effect. So that's great. The problem is that it's often infeasible, especially to do the random sampling from the population. So instead, I would posit that we often are in a situation where we might have what I would call a more typical experiment, where we enroll a bunch of people, but we don't necessarily know what population they come from. We kind of enroll whoever agrees to participate in our study. And so the sample selection bias might be quite large. The people in the randomized trial who agree to be randomized might not reflect the population of interest. So those delta S terms are big, but the treatment selection bias terms are still 0 because in this experiment, we randomize people to treatment and control groups. So again, this is sort of our prioritization of internal validity, where we do get an unbiased treatment effect for the sample of people in the experiment, but they might not reflect the population that we care about. We then turn to what I might call a typical non-experimental study. So this is one maybe where we have a large-scale data source, maybe electronic health records, maybe a national survey. So it might be quite representative of a population of interest, but we are not able to randomize people to treatment and control groups. And so in this case, it's sort of the opposite, where the sample selection bias might be small, but the treatment selection bias might be big. The final row shows what we might have if we do a really careful job with that non-experimental study, where we maybe have a quite representative sample, and we do a really good job of adjusting for observed confounders using methods like propensity scores or other design approaches. So overall, we might have small treatment selection bias and small sample selection bias, but we don't really still know the total bias because of potential unobserved factors. But overall, it isn't necessarily the case that the second row is going to have smaller bias for our population average treatment effect than other non-experimental study options. So thinking about population effects in this way, again, sort of forces us to think a little bit more deeply about how we think about the sort of relative ordering of different study designs and what sort of characteristics we really value for different purposes. So again, many methods, for example, propensity scores and other design strategies, aim to reduce that delta TX term in non-experimental studies. And there are some methods that aim to assess the sensitivity of results to an unobserved confounder. What we're talking about today are methods that focus on those delta S terms, sort of how big are they, how much sample selection might there be, and then can we use data and statistical methods to make them smaller, or maybe do sensitivity analyses about an unobserved factor that relates to sample selection. That's really what we'll be focusing on today.